the presentation I gave at NI Connect was called G Anywhere, Enhancing LabVIEW Development with a Cross-Platform Embedded Device Library. And I think that this is a pretty cool, let's say, kind of target for the LabVIEW community to consider building tools that can run LabVIEW G code on the Pico. Actually doing that involves a lot of computer science, compilation, and stuff. And I have this other kind of like side hobby project that I've been working on for many, many months, which is this kind of answering this question of like, could we compile G code and write that compiler in G? Like, what would it look like to write LabVIEW in LabVIEW? And the thought experiment currently is more at like a language level and what it takes to actually just do kind of I/O, not so much what does it take to build a whole editor for G code in G, because that's a huge undertaking. And we already have a really good G editor, which is LabVIEW, right? So I think considering what it would take to compile LabVIEW code to these other targets, like a Raspberry Pi Pico, would be a very interesting exploration that I think would benefit the LabVIEW community. And I think it'd be cool to write a compiler in G that could compile itself. How many of you guys have some form of kind of like computer science-y, software engineering, kind of like a little more formal background? Awesome, cool. How many of you guys have actually like created some kind of like compiler, maybe even like a very simple compiler? Yeah, sure. So we'll talk about what a compiler is, and there's kind of a simple definition of it. As a compiler, it takes something that's in sort of a more preferred form, like an upstream form, for whatever reason that it's convenient to be in that form. Maybe it's human editable, or one's tools save things in that format. And it transforms it into something that can execute, run, or be an input for something downstream, typically lowering it down to being able to run on hardware or in a different runtime system. So it's mostly just translating things into probably a more simple language. So I'm going to kind of skip over, or I'm going to rush through some of these parts. My presentation at NI Connect, I talked quite a bit about like what is the Raspberry Pi Pico, why is it cool, and then what would it look like to run code. And I actually gave a demo of doing that. I'll give some other demos here today. My Raspberry Pi Pico was in my backpack for too long, and it doesn't want to boot up right now. So fortunately though, they are pretty cheap. So you can get a Raspberry Pi Pico for like $5 or $6 US. The chip is $1 if you want to make your own board. So the idea of being able to run your LabVIEW code on that, like you could build just about anything, consumer product, what have you. I don't know. This is the pinouts. These are the pinouts for the Pi Pico. You can see it has a processor or microcontroller and USB connectivity and a bunch of general purpose I/O pins. It also has some cool capabilities in that it has, I think they call it PIO, programmable I/O, and it essentially is a little kind of loop that runs a state machine, and you can actually kind of program it on the fly too. And so that's nice because you can essentially implement hardware-timed communication protocols and other real-time things that run in hardware with it. That'd be something that'd be cool to be able to program in G, just like we could, run LabVIEW FPGA code in G. And there's a lot of cool add-ons for it, like little color LCD displays, et cetera. And I mean, even the displays only cost like, I don't know, between $8 and $30, depending on how complex it is. They also have good hardware connectivity. They have serial communication devices, CAN bus module. We were looking at things like this over the pandemic when the availability of a lot of hardware was not great. Actually getting Raspberry Pis and Raspberry Pi Picos, because they're produced in such great volume for the hobby market, meant that there was great availability for those. We just had to find a way to sort of get the data into our higher level LabVIEW applications. And the chip itself, the microcontroller, folks have created various different form factor boards with different type of I/O, different power consumption, different package footprint, etc. Some of them have like battery management on them. So, meant to be used in kind of like a sort of a mobile device that doesn't have to be plugged into the wall to work. I'm not going to go into all the details. So I'm not an embedded developer. I'm not a C programmer. I didn't take computer science, but I've been doing LabVIEW for a very long time and have decided to teach myself a lot of these concepts. So if anybody out in the audience knows a little bit more about these concepts than I do, feel free to chime in. So where it all started was the Pi Pico has a lot of different tool chains. There are a lot of different tool chains that you can write code to target. MicroPython, actually, you can then copy your Python scripts over and send them to startup, and they can access all the I/O. It's pretty cool. C, C++ are like kind of the standard way of doing it. And there's even great Rust libraries. How many of you guys have seen some of my posts about Rust recently? Cool. So I'm really interested in Rust because they have a pretty vibrant community. It's pretty, I'd say, like leading edge. A lot of big companies are looking for how they can start doing more systems and embedded programming in Rust. It offers a lot of benefits. And a lot of those benefits are things that LabVIEW also has. Very strict typing. It's compiled, runs very fast. And you don't have to, it protects you from a lot of issues with respect to memory allocation, deallocation, lifetimes, and security. So even really big companies now, parts of Windows, I believe, have or are soon to be shipping that have been built in Rust. And it's also very performant. Because of its strict typing, and you can't really see your broken wires interactively, it also is known for being rather painful to get the application to actually work. You write your code and you run it. Okay, there's this error. You try to fix that. You run it. Okay, there's another error. However, once it does run, you know it's going to run. And it forces you to deal with all these issues at development edit time, rather than having code is like, well, it compiles, it runs, let's ship it, and then realizing that it actually doesn't do what it's supposed to do. It has these undesirable, undefined behaviors that you didn't realize. So I've been kind of posting about some of the similarities of Rust and LabVIEW. And just today I posted on my blog with a little overview and a link to a real project that I helped work on at JKI to call a Rust library from LabVIEW and build a shared library, a DLL, from the Rust library with a very thin wrapper that just kind of exposes the APIs and the object references. And so we're using that at JKI in Dragon for reading the TOML, T-O-M-L, TOML file. It's a format kind of like INI configuration files. But that's a very good way to leverage code, libraries, tools in other languages that are robust, work well. Let's go. Okay. So a lot of this is kind of like, fun theoretical stuff. How you build something that is capable of building something just like it or slightly better. And what does that process look like? It's a very fascinating area of computer science that crosses over with math and even maybe a little philosophy. So I mentioned before that a compiler basically just takes something from the preferred form for working on it, whether that's a human or some upstream tool, and it performs a transformation that generally lowers it into something that can run on another system. And for us, running on a system means, running on a Intel processor in Windows, or it could be a Raspberry Pi Pico. It could even be running inside of like a virtual machine or a web browser. And all of the compiler technology books, tutorials are out there are really kind of designed around how do you compile a text-based programming language. And typically what, that process involves these steps. You have to read in the file. You have a bunch of kind of, let's say, keywords, if, then, else, let, and then you have your, assignment equals, or you have your comparison operators. You might have unary operators, binary operators. And so what these keywords, these tokens are, and you scan a text stream and you come up with a long list of these tokens and their positions in the file. And then what needs to happen is we then kind of look at that stream and how they're kind of related to each other. We see, oh, this is a variable name. Oh, that's used in more than one spot. They're related to each other. And we come up with, through that syntax analysis based on sort of the rules of the language, we come up with an abstract syntax tree. And this is commonly referred to simply as AST. If you have Python, you can import AST. And once you have the AST module imported, and I'm not going to get the exact functions or classes, right? But you do something like, AST.load from string. Or you say like, my code equals AST.load from string. And then you can feed it some Python string code. And what it gives you out is an AST object, which is probably like a module for that code. And you could do things like you can with LabVIEW scripting. Right? You could say, okay, what are all of the methods or functions in this code? And it would give you a list of them. And you could, once you have the list, you could iterate over them, get their name. And so now you can programmatically interact with the code. Once you have a software data structure, this abstract form of the program that kind of has the semantics, syntax of your language kind of built into it, then you can do these transformations to generate code in some other language that's maybe a lower level. So if this is like, who's had the pleasure of writing like assembly code? Okay, a lot more people than me. you could write something that generates assembly code from this AST if you know how to do things like create a register for storing data. Okay, that's kind of like a variable, and then you can read from it, you can write to it, you can perform an operation on this variable and that variable with these registers, so you can programmatically then generate that code. And there's a whole lot of really amazing infrastructure that we'll talk about that text-based languages use, including what LabVIEW under the hood uses. LabVIEW uses a compiler architecture in LabVIEW's compilation architecture called LLVM, which used to mean like low-level virtual machine, but now it's just the LLVM organization or foundation, and they have a big mono repo that you check out, and then all the different pieces like use the other pieces, and you choose which ones you want, and you can compile them. But at the end of the day, there actually is like an LLVM format, which is an intermediate representation that's sort of like a level above assembly, and uses something called single static assignment. You can assign values to variables only once. You can then read from them multiple times, write once, read many, and then do operations on it. And so that tool chain is then often used by nearly all the major programming languages that you guys have heard of. Rust, Python, Swift, whatever it is, Julia, these all use the LLVM toolchain. We'll talk more about that later. But the idea is we just want to get it into a form that it can be run by some other machine and perform the work in a way that adheres to what we've sort of designed in our language. So if we get back to this idea of what would it look like to create a G compiler in G, we're actually pretty fortunate that LabVIEW doesn't really have these upstream text-based parts. So it's not text-based. It's stored in a binary format, and when you load it, the scripting API gives you access to all of the objects, just like you would in AST. So the point here that I like to make is, that abstract syntax tree, that looks a lot like a graph. Nodes, edges. So graphical data flow, actually there's a lot of stuff we don't have to do to create a G compiler in G. So what does it actually need to do? So a G compiler needs to generate code from a program's data flow and control flow graphs. These are commonly referred to as other acronyms in the kind of compiler lingo, DFG, CFG. The interesting thing, as I've been learning more about compiler technology, one of the things that engineers working on these tools are really in need of is a way to visualize graphically the data flow of the program once it passes through those first couple steps and it kind of gets into the AST format, and then they're trying to compile it down. They want to see what the code looks like. So again, it's like we're so lucky we get to see those relationships as we're writing the code. So if we're going to build a G compiler in G, because a compiler can really mean anything, we can choose what we're going to compile to and why. And in making those choices, different things kind of come to mind as kind of like driving needs, requirements, good ideas. And for starters, I really was gravitating towards this idea of translating G into Rust code as an intermediate representation, not as something like, oh, I can just export my LabVIEW code to Rust and no, it's a Rust project. Ideally, you wouldn't ever touch the Rust code, or at least not the parts that are generated by a compiler. It's just a convenient target. And by convenient target, the different things that I think about when deciding on a target is, well, how hard will it be to map sort of the functionality of graphical data flow into that execution environment, that language? Does it have the features and the richness that are needed to actually translate? If you're translating a spoken language, you're like, oh, there's no word for that in our language. We kind of say this. Well, you lose something important there, and we don't want to lose anything important. So this next part, I'll mention another thing too about Rust. There were enough good reasons for me to want to learn Rust and interoperate with Rust that deciding to transpile to Rust also felt like, getting, cutting two carrots with one knife, so to speak. The other aspect too is because Rust has such great support for these embedded targets, and it actually has a lot of good parallelism and concurrency libraries, runtimes, frameworks. It's a worthwhile place. I think we'd be able to do what we want to do. Okay, so this is a simple LabVIEW example, nothing tricky there. So what would that look like in text-based code? So in text-based code, as Fabiola was saying, the variables are like the wires. And that's certainly true. So what we need to do is when we have a constant or a data source, we are essentially, we're creating a variable that represents the wire flowing out of it. So this, I seem to have lost my mouse, which I don't know if there's any way to get it back. But you guys can see up there, the wire flowing out of hello, the top wire is represented by my string 1. My string 2 is the bottom wire world flowing into the concatenate. Just for fun, we created a little concatenation function. It's off screen somewhere, but when you call that function, it concatenates those two strings. And then finally, when we want to print it, we call another function, myPrint, that we pass in the output of the concatenate function, which is the myString3. MyString3 is the wire flowing out of the concatenation function into the print statement. So this third, let's say, line of code where we call the concatenate function, we're taking its output and assigning it into that wire's value. And then finally, we pass the wire, myString3, into the print function. And we can, if we want to, can sort of rearrange this. At least I can in my screen capture program. I can just copy and move the pictures of the code around, because I'm not limited to lines of code here, and we can kind of see what that data flow looks like. Okay, so I think what I'll do is I'll just show you guys a demo of some of this stuff working. Any questions before I go into a demo? Okay, let's see if we can do this. So for this project, or for the G compiler in G, one approach that I've taken is we're not using scripting to parse a block diagram. We're actually calling some special VIs that when they are called, they essentially create that that graph of the data flow. They create constants, a function calls, and wire everything up into a graph data structure behind the scenes rather than scripting. So let's turn this back to hello world. We can run that. And I mentioned that it generates a graph behind the scenes. So I have this little kind of debugging tool that uses GraphViz. This uses a cool library called Graph Builder that Cyril Gambini has been working on, and also that is used, I think, by AsciiDoc. Yeah, AntiDoc, yeah. To kind of draw pictures of class diagrams and stuff. It's a cool library. And so I'm going to hit this button. And what this is going to do is it's going to take the generated, okay. And wow, okay. So what happened when I hit that button is it took the generated Rust code and it sent it to this website, and it actually passed it as a URL parameter. And this website, which is called like the Rust Playground, is a place where you can actually run Rust code, simple snippets. And it's a great place for people who want to work together and like share examples. You can click share, it'll give you a URL to this snippet of code, and you can give it to your colleague and say, or in like a Discord chat or web chat, and you can say, oh, here, check out this example. It does what you want to do. And they can pop it open, and then they can hit run, and then hopefully they see in 1.5 seconds, 3 seconds, hello world. Cool. And just to show you that this is actually working, my cap or shift isn't working well. There, hopefully I did that according to the trademark guidelines of the GDevCon Association. Okay, and so now if we hit that button again, we see it was updated. All right, and so what we have here is LabVIEW running in a browser. But in all seriousness, this is it's pretty cool when things can be distilled down to this level. They can be run just about anywhere. Let's take a look at some of the under the hood stuff. So I have a little bit of kind of tooling here that is doing some of the compilation steps behind the scenes. But if I just explore down here, I'll show you kind of what's going on under the hood. And I'm gonna, I was gonna try to open it in here. I'm just gonna open a PowerShell. Okay, great. And then, okay, there we go. If I type Rust C, which is the Rust compiler, and then hello Sorry, my shift key isn't working. It's going to be the end of me. Yeah, if we type this command, this is going to compile that Rust script, which is just a text file with the stuff we saw in the web browser. And it's going to generate a hello world .exe. And so if I run this now, you can see the output. So the ability to run also console applications is a very useful tool, especially in like systems programming or building tools that run on like a server, maybe a build server or something, or that just need to like read one file in and dump another file out. It's very powerful. And again, this Rust file can literally run anywhere that you can compile Rust to, and they're always adding new targets all the time. So let's look at another example too. I'm going to open the hello prompt. Okay. So what this is doing is this is taking a string and it's calling this print function. And this is similar. This is just a little kind of control flow wire that just kind of tells the G compiler that we want this to run after this. It doesn't actually get any data. It's just control flow. So it's similar to like using arrow wires to control the order of execution. So after we print the prompt, we will then call readline. And readline is waiting until it gets a carriage return line feed, and then it returns that data. We will then trim white space, and then we will format a nice response that says hi to this person. So I'm going to run this, and I'm hoping what happens. Okay, so I set up a little helper that essentially will then run the program after I do this. You can say, okay, Jim. Oh, I should add a wait. Let's add a wait and see if that works. Oh, need to pull my favorite tool, quick drop, over here. Which reminds me, if you see somebody here that's written a tool that you love, make sure to tell them the ways that it's helped you code. Okay, so I'm going to just wire the control flow in here, and then I'm going to do a wait, and we will wait. Let's wait 2 seconds. There's a lot of malleable VIs too, so things are sometimes a little bit broken. So hopefully, I don't know what happened. Okay, so there's a bug somewhere in my code. What I could do, let's see if this works. Oops. I'll do another read line so that hopefully it'll just wait until I hit return a second time after it tells me hello. And if that doesn't work, I'll just open a command prompt and do it myself here. There you go. So that worked pretty well. And so it said, hi, Jim, and it's waiting for me to hit return. If I wanted to make this nicer, I could also have it print something like a new line that says, hit enter to be done with the program, hit enter, we're done. So what you guys are seeing here with these kind of like weird thick wires and kind of green icons is something I haven't really talked much about, and I plan to talk more about kind of through kind of the end of the year. And want to make a lot of what we're working on open source for the community. This is not directly related to compilation, but once we start getting into the idea that we can, compile, we have libraries for, creating and manipulating graphs. I really see a lot of potential for the community also to do a lot of innovation at a language level in G, and I'd like to see that moving forward. But basically, each of these nodes doesn't actually execute code. It's just a representation of code that you want to execute. And when you run it, it then dynamically constructs the abstract representation in the data structure that can then be manipulated. So I call it abstract G. And we'll talk more about that. I'm not going to go into that much more today, but definitely stay tuned. Let's see here. Okay, so getting back to the presentation, this is cool and stuff, like we've done Hello World, but we're actually still a ways away from having, let's say, a practical application or being able to create a program that runs in a way that expresses the full capability of LabVIEW's parallelism, or actually even runs in the way that we would expect. The example that I showed just did a kind of quick top to bottom, assign a variable, call a function. What do we do when we want to call two functions in parallel at the same time? Text-based programming languages, they've built kind of tools to do that. And it's kind of this weird place that we're in, even utilizing kind of the best in breed compiler technology, aside from like the FPGA synthesis for targeting those parallel devices. All the compilers, expect that they need to write code that's going to run in these little machines that can only do things one at a time. And then they have then built frameworks for doing cooperative multitasking, which means that, all the parts of the code kind of agree to tell us when they're idle so that the runtime, the engine, can have other bits of code working while some other code is waiting. Has anybody here played with async and await in Python, async IO? A little bit. So let me see if I have any examples here. Okay. So async and IO, 5 minutes. Okay, so I'll try to jam here. So text-based programming languages kind of have a few, maybe more different kind of tools or paradigms for dealing with concurrency. The main idea is one can declare kind of like a thread and blocks of code that aren't sort of executed when they're evaluated, but they get sort of assigned to the thread, and then you can choose to then run the thread, and that actually executes the code. And so the code doesn't necessarily execute top to bottom, but you're sort of constructing tasks that you then have a reference to. The variable is the reference to the task, and then you take a bunch of tasks and you invoke like a run on them, and then the engine runs them. The functions and things that you can call have to be declared as async in order to be able to be run by the engine. It's sort of, it's this whole separate set of functions for a lot of different like standard libraries have to have async counterparts because it requires a lot of cooperation. But I probably won't have too much more time to go into this, but what I'll say is, so right now what I've been working on is how to do clumping. And the idea is that if you have parallel snippets of code, how can we actually compile them in Rust using Rust's, well, it actually did print out a couple. I'm getting the spinning wheel of your presentation's almost over here. But we could see in that graph that I was showing you, it has these dotted boxes around everything. I've been experimenting with how to create a clumping algorithm that will essentially wrap pieces of code and group them together into things that can run asynchronously. So certain functions like wait milliseconds, if you have two of them, you know because it's a wait millisecond that you can't just call them back to back and expect them to run in parallel. Those functions have to be known by the compiler, the language, as async. And so during the compilation process, we build a graph of the interconnectivity of all the nodes. And then we have to do passes where we assign nodes into these different task groups where there's one and only one async function within a task. And then what we can do when we compile them, we can compile them in a way that kind of ties together their data flow dependencies. So I won't show you too much more of that, but what I will say, there's a lot of interesting new areas of development. I'm going to be sharing a general purpose graph library that I've been working on, which uses maps and sets for storing the objects and connectivity of the graph nodes and edges and attributes. Working on these passes for doing kind of clumping under the hood. Also, I wanted to mention all of the languages that are using LLVM, which are practically all of them, have sort of developed their own slightly higher level than LLVM intermediate representations, which they have called like mid-level intermediate representation. And the LLVM organization saw that every language had to do this, and they started to define a higher level intermediate representation. The interesting thing about this, so it's a text-based language, which allows kind of in a very abstract form, defining the names of operations, the data inputs, the data outputs, the data types, and all the rules of your language. They call this a dialect. The MLIR toolchain actually ships with several different dialects. A lot of it's aimed at machine learning. What's interesting about this is MLIR I'm not sure if it's by default, you have to declare it, but essentially nodes that execute code can have multiple inputs and multiple outputs, and they are just implied to be running in parallel with each other, and their control data flow is determined by the interconnectivity of the outputs and inputs. And it's like, whoa, that's kind of like LabVIEW. So it's pretty interesting that that's the direction that they've been going, and there's actually work being put into tools for visualizing it. It still doesn't deal with the problems of threading, unfortunately, because threading and async stuff tends to have to rely on the execution target, the operating system, the microcontroller, and the C libraries for how it, does threads. So typically, even though MLIR sort of is in a lot of ways like G, one would still have to kind of deal with all that async thread management stuff that I don't necessarily consider myself an expert in. And then also too, I think evolving G as a language. So I'm going to continue posting about this on my blog. Create.vi is actually the domain name. It's easy to remember. I showed the announcements, but I think what I'll close with is in the topic of how can LabVIEW be competitive or stay competitive, or let's just even say continue to stay relevant? How can all of our careers stay relevant? I think it involves learning other tools and finding out kind of what's in common, what can we leverage, and also too, I think kind of taking for us to kind of take a sense of responsibility, for LabVIEW. I think N.I. and its future owner, if there's an acquisition that happens by Emerson, they're going to have to focus on their business drivers. May or may not align with, overlap with things that we care about to keep LabVIEW and G relevant. And so I would really love to see a lot of these, libraries and tools be developed by the community. Not every LabVIEW developer is, going to be working on compiler technology. However, I do think that, moving forward, it would be good for all of us to start exploring these tools. The goal, for this is not really to it's a lot of work creating a great G editor. It requires UX designers, product managers, and it's not something that just software engineers that write code can do well. It takes a lot of work in a big team. And so, LabVIEW is a great G editor. And also, I would love to see more of LabVIEW, the compiler technology, the under the hood stuff, written in G. I think over the years, that's been the dream of a lot of people at N.I. over the years. And I kind of think that there's, in terms of kind of general timing with, the shift away from NXG and what is current gen going to be like, we've got these great tools like interfaces in LabVIEW. I think the time is really, now for the community to start, deciding, what does it want for itself in the time ahead. So create the future you want to see, you know where to find me.
A special thanks goes out to Kevin Shirey, Quentin Q. Aldridge, Mark Balla, and Jeff DeBoer for their help in filming. And of course, this GDevCon N.A. 2023 wouldn't be possible without all of our sponsors. Thanks.